There's a lot of statistics made on this internationally and shared among countries. So for coal-fired power plants, they kill 1,000 times more people per terawatt hour of electricity than the average nuclear power plant.
That is including this Chernobyl event. And,
yes.
Welcome to our Energiegespräche. This time I'm in Copenhagen at Copenhagen Atomics, and I meet Thomas Cem Pedersen. He is a founder of the company Copenhagen Atomics, and they are producing a new type of reactor, and so it might be very interesting to learn about the thorium reactor. And he is by education a Master of Science Engineering, and he has more than 50 years experience in software and hardware industry, so he is one of the group controlling that company. So the first thing I always like to ask is, what was your way to energy? Why did you go to the topic energy?
Yes, energy is really, really important for our society. I mean, we actually on our T-shirts we have a statement on the back saying energy equals prosperity, and it is because we cannot have a prosperous society without having access to energy. And the best way to explain that is for, tens of thousands of years we humans have been here on the planet, and it was really tough life to survive. And then we found out how to harvest energy from coal first and then oil and gas later, and it completely changed everything. I mean, now we all live the type of life that most of us live is better than what kings had access to just 300 years ago. So energy has really changed what it means to be a human on this planet. And of course, we also, when we started using energy, we were 500 million people, and now we're 8 billion people. So we also, because we have access to energy, we can have a lot more people. So that's why I got interested in it. And then there's a little bit of different story how I discovered thorium, but I'll wait.
Yeah, we'll go into that in detail. So yeah, so what you did is you started a company. And so what is Copenhagen Atomics? So this company is sited here in Copenhagen. And to know, Denmark is not well known for nuclear power. It is known for theoretical physicists. There's a Copenhagen interpretation of quantum mechanics for the experts. But what is the basic idea of this new company here?
Yes, so it's correct. We were there. I started something called a meetup back in 2012, where a lot of people came to a bar or a cafe and discussed different energy solutions. And particularly this meetup was called Molten Salt Reactors and Thorium. So people came to hear what is that. They've read maybe a little bit about it on the internet, and they didn't quite know what it was. And then there was this meetup where they could come and drink a beer and get somebody to explain what it was. And in the beginning, not a lot of people showed up, but later we had more and more people coming, so more than 100 people showing up for those meetings in the end before we canceled it. But there was a lot of people, and out of that group of people, actually 2 companies were started, and Copenhagen Atomics was one of them. And so it started by 4 people, so we have 4 founders, 1 physicist and 3 engineers. The other engineers are sort of chemical engineers and material science. I come more from a background of software engineering, electrical engineering, and mathematical modeling. So a lot to do with sort of how do you simulate these types of reactors. We sort of knew that it was possible to get energy out of thorium, which is a metal. But we didn't quite know how to build the machine that could do that. I mean, okay, it's possible when you do the math on a piece of paper, but how do you build the machine that can actually do that, take the energy out of the thorium? And I guess this is what we're still trying to figure out, but we know now, and now we just need to build it.
Okay, so you had already the idea. I think you have read about these American experiments in the 60s about the thorium reactors. Yes. And so you were aware that this technology basically works in some way. And so now, if you have a good idea, the problem is always you need resources, you need capital. Yes. How could you start from the scratch, from bootstrap?
Yeah, that was not easy. So we recognized that it was possible to get all this energy out of thorium from physics.
Yes.
We also recognized that in the 60s they had a reactor in the US that were supposed to be able to do something similar. I don't want to go into details, but it's been tried many times to put thorium in classical reactors like the ones we use for uranium.
Yes.
And it doesn't give any, it doesn't work better than uranium. It's almost worse. So it has been tried many times, and every time people tried it, whether it was government sponsored or whether it was a company trying to start, it failed because the economics doesn't really work if you put thorium in solid fuel reactors. And we knew that all the way back there in 2012 and 13, but we couldn't quite, we couldn't prove it with simulations, but we've done that since then. But then we knew that there was this really brilliant guy called Alvin Weinberg, who also helped invent most of the other types of reactors we've had in the world. He used to run something called the Oak Ridge Reactor School back in the 50s and 60s at Oak Ridge National Lab. And this Oak Ridge Reactor School is where most people got all their ideas of different reactors, whether it's fast reactors or molten salt reactors or high temperature gas cooled reactors. So all of that were sort of developed at that reactor school where he was the main teacher or whatever. Yep. Anyway, so he also came up with his molten salt reactors, and molten salt reactors can actually make thorium economically viable. And we learned that. I mean, also for me, it took, I think, 3-4 years to understand that and understand why. And it's only when you do the simulations that you really understand. So you can sort of adjust the different parameters, and then you can see, okay, if I change this size or this type of liquid or whatever, then I get this and that property.
So the point is, you had already the idea from Weinberg and others who had gone into the technology, so you knew there's a reactor you can build. And now the question is, what is a thorium salt reactor? We should go a little bit into that.
Yes.
Because at high school you usually learn about uranium. Uranium, if you're a little bit an expert, you know uranium-235 is giving you the right material for a normal reactor. What's going on with thorium? So you're using thorium. That's a very different element.
Yes, correct. Thorium cannot be used directly in a nuclear reactor. It needs first to be converted into something else. You're absolutely correct that we have this uranium-235 in nature, which we can dig out of the ground, and it can be used in a reactor directly. So that's great. But we've had, there's only been the CANDU reactors that can actually use it as natural uranium. Yeah. For all the other reactors we have in the world, you need to enrich the uranium. And that enrichment process was discovered or developed during the Second World War through the Manhattan Project. But it was very expensive, so it was not until later in the 70s that it was optimized to become fairly it's still expensive, but it's better. It's okay. Not as expensive as back in the 50s to enrich uranium now. But anyways, thorium cannot be used directly because it cannot create a chain reaction where you get enough extra neutrons that it can sustain the chain reaction. Yep. So you need to convert thorium into something else, and you can do that inside a nuclear reactor through some process that I don't want to explain, but it is converted into something called uranium-233. Okay. Which is an element or an isotope that does not exist in nature. So uranium-233 turns out to be an excellent nuclear fuel, even better than the uranium-235. And you don't have to enrich it because it comes from thorium. So in the reactor, when you convert the thorium, you already have the uranium that you need. But of course, the whole problem now becomes, instead of having an enrichment problem, now you have a problem where inside the reactor, you have to convert enough thorium all the time so that you don't run out of uranium-233. You need to convert enough uranium-233 so that the reactor can keep on running.
Okay.
And the problem of doing that is called the neutron economy, or you have to look at the neutron balance. How is the neutrons consumed or used inside the reactor? And that is really, really important. And that they couldn't do in the 60s. They didn't have enough simulation tools or enough knowledge how to figure out how to optimize the reactor core in a way where they could balance this this neutron economy so that they could make basically what is called a breeder reactor. That's when you make more new fuel than what you consume all the time. An isobreeder is when you just make enough, the exact same amount as what you consume. But of course, ideally you would want to make a little bit more so you're sure you don't run out of it.
Okay.
So that's the type of reactor we want to develop. And Copenhagen Atomics is not the only company who wants to do that. There's been a number of other companies, and I just want to mention one of them called Flybe Energy. I think they are onto the same idea as what we're trying to do. They're trying to figure out how to optimize this, but they have tried some different routes than what we're trying. I mean, in order to have a great neutron economy, you need to slow down the neutrons. That's called thermalization, or
so it's going slower.
Yes, and you need a moderator. It's called a moderator to slow it down. And the best two moderators there's 3 good moderators in this world. There's graphite is one of them, then heavy water is another one, and light water is the third one. The problem with the light water is that light water will also capture some of the neutrons. So it's good at slowing them down, but when it slows them down, it grabs like 10%. It's not 10%, but something like that.
So, but you lose some of them.
Yeah, you lose a lot of them. And that's not good if you want this thorium cycle where you convert thorium into uranium-233. So light water doesn't really work. So you're back to either graphite or heavy water. And we chose heavy water, and this other company I mentioned, Flybe Energy, they chose graphite. And it might be possible to build a reactor with both. That works. But of course, I'm in favor of the heavy water.
Okay. Yeah. So the one thing is now we have learned is that thorium is another metal in Earth. Is there abundant material around? So the question is always, especially in this green area of politics, is there enough for long-term usage? Yeah. Because uranium-235 seems to be a little bit, only a few, 0.7% of a natural uranium is useful. So you need to have huge mining. So where can you buy thorium, or where's the resource thorium?
Yes, you're absolutely right. The comparison, uranium-235, which is what we use in all reactors today, it's quite rare in nature. We can find it and dig it up, and we're actually really good at finding it. It's about as rare as platinum in the Earth crust. But thorium, on the other hand, is much more common. Thorium is in all countries of the world. Thorium is about 1,000 times more common than uranium-235. So there's lots of it. And also, already today, when we mine for other materials like copper or iron or gold or rare earth materials, stuff like that, we get lots of thorium out of the ground in those mining operations.
They come together.
Yeah, they come together. And the mining companies get lots of it out of the ground. But there's no market for it today, so they put it back in the ground.
So I've heard about that. The amount of thorium you need for your lifetime is you can buy for $100.
Yes, correct.
That is absolutely
yeah. That's also what got us started. When I told you back in 2012, 11, 13, this was when we realized, this thorium is inexpensive. Now we just need to figure out how to build that machine. And I remember back then when we had discussions, we said, it doesn't matter if it takes 10 years or 100 years. I mean, it will really benefit humans if we can just figure out how to make that machine. It's a little bit like making the airplane. When they made the first airplanes, there was lots of people who said, no, it cannot be done, it's impossible. But then the bicycle guys in the US found out, and there was also other people tinkering with airplanes. But then eventually they found out how to do it. And I think we are also definitely on the about to show that we have found a way to do it. Of course, the first one is not going to be the best one and the most optimized one. Just like any other technology, it will take several decades to really make it perfect. But once we've shown that it works, then I think a lot of capital will come along and say, okay, let's try to make this better.
So we know from physics that really only $100 buys you a whole lifetime energy if you are able to convert the thorium into the electricity or whatever. And now the second thing that is, so if we are in a standard reactor, we have this fuel rods. They're going in there, staying there maybe 18 months or something like that. Then they're replaced, and for some reasons a little bit complicated replacement process. And so the reactor has to wait 1-2 months until it's reloaded. Now, in the thorium molten salt reactor you built, you are not working with fuel rods, you are working with a molten salt. Yes. What is a molten salt?
Yes, a molten salt is, the easiest way to explain this is the table salt you put on your food.
Yep.
I mean, if you take that and you try to melt it in a pot, it melts at 800 something degrees.
Yep.
And it becomes a liquid where you can actually, it's transparent, you can look through it. So it's almost like water, but it has twice the density as water, so it weighs like 2 kilos per liter. Okay. This sodium chloride is table salt. We cannot use that in our type of reactors, but there are other salts made in a similar way, which just, they use different elements, but they look the same. If you have them, you can also make them into crystals and put them on the table. You should not eat them, the salts that we're using, because they're made from fluoride, so lithium fluoride and thorium fluoride, for example.
Okay.
So they are, fluorine is a little bit toxic.
More
so
active,
yeah, so don't eat it.
We want to eat it,
no. Yeah. But it's actually funny because sodium chloride, chlorine is also toxic, but it's sodium chloride, it's okay for the body. The body has adapted because it's in salt water. Yeah. So it's all around the earth. So all the fish and all the humans had to adapt to that. But we don't have lithium fluoride in all around in nature, so we didn't have to adapt to that. Okay, so that's why it's toxic for the body. It's actually not sort of from a chemical standpoint. It's not worse.
Yeah. So we have first we have a salt, and now the thorium fluoride salt. That is a similar salt, but yes,
it's also transparent.
Yeah, it's transparent.
And it's liquid, just like water when you melt it.
Is the density? What's about the density?
Yeah, so because thorium is a very heavy element, it becomes dense. So it's a little bit more than 4 kilos per liter.
Okay,
so it's a little bit more heavy than table salt.
Yeah, I understand.
But it's still transparent, and it's
fluid.
The viscosity is similar to water.
And the melting point?
The melting point is lower. That's good because 800 degrees is quite high.
Yep.
So for these lithium fluoride, thorium fluoride salts, the melting point is down around, see if I can remember, 550, maybe a little bit lower.
Something like that. It depends on the details. So you can handle that in a typical vessel, whatever where you put that. Now, we have learned that salt is usually not good for metals. So we have salt, if a salt is on the street in wintertime, our car gets rusted.
Yes.
And now the problem is if you put that thorium fluoride into a vessel, then the question is, how long can stay the vessel?
It's absolutely correct. All these different salts, all of them are corrosive. To a different extent, because it's all chemistry. And you're absolutely right that salt water is corrosive, but we still have ships made out of steel. So how does that work? We have had all these giant ships sailing around the oceans in hot days and cold days, and they don't corrode away. And of course, the reason the way they solve that is they have some really good paints, and then they also have this zinc, like chunks of zinc that will corrode before. So that's like a galvanic thing where the zinc thing will corrode before the steel.
Yeah.
So that's the way they make sure the salt reacts there first. So you can do a similar thing with molten salts and reactors. But actually what we found out is I should also say that there's been a lot of research in molten salts and corrosion at the Technical University of Denmark. And one of our co-founders, Thomas, that's another Thomas, he did his PhD there in that group where they did corrosion studies for several decades. So he knew a lot about how to avoid getting corrosion. And it turns out with fluoride salts, one of the main problems is the moisture, because these salt crystals, they will trap water inside. So you have to sort of, pray to the God and get that water out of the salt crystals. Otherwise, you get corrosion. And we've developed a method here. They already started in the university, but we have continued to develop that. And we found a way to get almost all the oxygen and all the moisture out of the salt crystals. And that that's the main thing for us. That removes like 99.9% of the corrosion.
Oh, that's really great. Yeah.
Then you're back to this situation where the ships, you can put on some paint, and then it's good for 25 years. In our case, removing the water and the moisture or the oxygen, that allows us to use regular stainless steel with these salts for roughly 5 years. So it's not like the corrosion is completely zero, but it's low enough that you can use, some steel for 5 years and then you can replace it.
So the interesting point is you are replacing the vessel where the salt, the liquid salt is inside, but you keep the liquid, you keep the salt.
Yes, because the salt is very expensive.
Yeah, okay, so thorium, fluoride, and all the other ingredients, that is the expensive resource of your reactor. And so you have to change the bottle sometimes.
Yes, exactly.
Okay. Now you say the lifetime is about maybe 5 years. So it depends on details.
It depends on how thick you make the wall, but the wall thickness also has an influence on how well the machine works. So if you make the wall really thick inside the reactor core, it will not work because it will damage the neutron economy. And if you make the wall thickness very thick inside heat exchangers, for example, also they will not work well. So you cannot have like 5 or 10 centimeter thick walls. So you have to have fairly thin walls. But the good thing is that there's no pressure on these reactors. The classical reactors have very high pressure, and therefore like walls are thick as this,
10 centimeters,
like 10, 20 centimeters. But in our case, it's just room pressure or atmospheric pressure. So no need for thick walls other than for the corrosion. But if you can get the corrosion far enough down, then you can use like 2, 3, 4 millimeters thick walls and it's okay.
So the interesting point is that so you use more or less standard steel or corrosionless steel. And then you can build that. Now the shape of your reactor. So that today we have nuclear power stations are huge buildings.
Yes.
And they have huge vessels where this high pressure is in there. We have 70 bars or even more. And the real danger in nuclear power stations is that they, for some reason may explode because there's something going wrong. And with a high pressure, then that's dangerous. So we have this concrete buildings, spheric shape and stuff like that. Now, if you don't have a pressure, then that relaxes a lot of technical problems.
Yes.
Now, the lifetime, the size of these systems is not as large as we are used for nuclear reactors. Usually we have something like a 10 meter or something like that. How large is your nuclear reactor?
Yeah, so the reactor core we have taken a lot of patents on a special new design of reactor core. We call it the onion core. The diameter, it's like a ball that is 2.5 meters in diameter. So. And we've done a lot of simulations to find out, can we make it smaller or should we make it bigger? And it turns out that the 2.5 meters is about the optimum. If you try to make it much smaller, then it won't work. Then you don't have enough fissile inventory in order to make it run. And if you make it much bigger, then the balance between this thorium and how many neutrons the thorium capture and the fuel salt becomes wrong, so it's not optimal. So it's about the right size, 2.5 meters. There's some other, if you adjust the chemical compositions of the salt or the temperature or something, you might want to change it like a little bit up or down, but it's like within 10 centimeters
so
up
it
or
is
down.
More or less that's the size of 2 and something meter. And so that is fitting into a container.
That's what we found out. Oh, this is the same size as a regular shipping container, so you can fit it in there.
Yeah, that is, and the idea is in your company, as I understood, is that you produce the nuclear system in a production hall, in a serial production on the long term.
Yes.
So it's not on site where you produce it.
But that has been a hope or a dream of all nuclear physicists for many years. I mean, even the old reactors, there's been a lot of discussion. if we can manufacture things in a factory like we do with cars and airplanes, then it can become much more efficient. You can the people can learn to do the exact same thing over and over again and remove the small errors that they make and make it more efficient and faster and less expensive, and remove some of the make it a better quality. So this has been a dream for many years for many companies to make an assembly line production of reactors. The problem, like you said, the old classical reactors are really big, and they're much bigger than an airplane and much more heavy than an airplane. So how can you make that in a factory and transport it somewhere? They couldn't do that. So they said, okay, let's build it in sort of units or compartmentalize it and make sort of modules, and then move those to the side, and then put together those modules on the side. Then maybe we can make it in a factory. But because we were able to put it in a shipping container, we don't need this thing where we have to move a lot of modules to a site and then assemble those modules on the side. We can make the whole thing in the factory, and then it's done. You don't need to do any work when you get to the site. You just plug it in, and then it works.
Okay, so you can build the reactor and the more or less management of this reactor. There's some Fintiles have some. Then the question is, one of the points in nuclear reactions is you are splitting atoms.
Yes.
So you have then the fission products, and they are usually radioactive, beta decay processes. And so people are also worried about what happens with the containment, what's going on there. What happens here with the material that is inside the reactor of a radioactive containment of products, of the fission products?
Yeah, you're absolutely right that anytime you want to split an element, you get what's called fission products, 2 or 3 different, usually 2 different new elements, and they are always radioactive. No matter if you use something works on thorium or uranium or plutonium, or even in fusion you also want to split lithium-6 to get tritium. That's also radioactive. So I mean, in any reactor system like this, whenever you split something, you get radioactivity. Yeah. And it's actually really radioactive right after you split it. Okay. And you're right, it's a beta and gamma radiation usually, a lot of it. So you don't want humans to be near that. I mean, it happens inside a machine, and you don't want humans in there. But of course, it's the same. An electrical motor, you also don't want humans inside the electrical motor.
No, not really. So the point is now, in a standard nuclear power station, in the reactor, you produce this fission materials, and they have produced their own heat. So that is called the rest heat of a reactor. So we cannot shut down a normal reactor. How is that situation handled? How can you shut down a reactor, and how is this different to a thorium reactor or a molten salt reactor, to a standard uranium rod reactor?
Yeah. In a standard reactor, you have these control rods, which is basically some rods that you put in the reactor core that captures enough neutrons so that the chain reaction will stop. Yep. And then you say, okay, now the reactor stopped. But you're absolutely right that there's this decay heat that continues to be produced even after you stop the chain reaction. It continues to make this decay heat in classical reactors and also in thorium reactors. So it always happens. And in thorium reactors, it's about the same amount of decay heat. The rule of thumb is right when you shut down the chain reaction, it's roughly 7% of the power you were running. So if you were running at 1 megawatt and then you shut it down, then it's 70 kilowatt that you have as decay heat right the instant when you shut it down. But it quickly decays. So already after 1 second, it's down to 6 kilowatts.
Really fast.
60 kilowatts for a 1 megawatt. Or 6%,
something like
that. And then after 1 hour, it's down to 1%.
Okay.
So within the first 1 hour, it really decays. But then it doesn't go slow. Then all the way out into 1 year, you still have some decay heat being made. And of course, if you don't remove that heat, then you can melt things. And this is what is called a meltdown. So in classical reactors, because they use water as the coolant material, and then if the water evaporates, that's when the steam escapes, then suddenly you don't have anything to cool those fuel rods. And this is what happened in both Chernobyl and Fukushima. Then these fuel rods become really, really hot because they still have that decay heat for many months. And then eventually they melt, and it's molten metal basically. And then it drops down to the bottom of the containment, and it sits there as like a big pool of lava. It looks like lava. Yeah. And then it's difficult to remove, because now you have this chunk of really hot and very, very radioactive stuff, and it's not easy to remove. You don't have a crane or anything that can pick it up. But it's not dangerous, actually. I mean, this molten thing there that happened in Fukushima, it didn't kill anyone. It's just expensive to
remove it.
Yeah, to remove it. But
so now how would a situation of a meltdown look in a thorium molten salt reactor? Yes. So molten salt means it's already hot.
Yeah, and that's actually a big opportunity, because you cannot melt it. It's already molten.
Yeah, okay.
So what happens with this decay heat is it will heat up the salt. So if you have the salt, let's say you start at 500 degrees. Yeah. And then now you have the decay heat. If you don't remove that decay heat, then the salt itself will heat up. But the heat capacity of the salt is really big, so it takes a lot of time, like many days, to heat up the salt. And then, of course, whatever containment you have, let's say you have a stainless steel tank where the salt is inside, eventually it can get so hot that you start melting the stainless steel containment. And then it will run out. But this is where it's important to have some what's called passive decay heat removal. Basically, you need to put somewhere where the heat can, go away, so that you won't melt the containment. But in almost all molten salt reactor designs, there are 3 layers of containment between the salt and the nature, and we also have that in our reactor. So you have 3 barriers that would need to melt in order for it to escape. And in our design, we have passive decay heat removal in all 3. And I don't think we will ever see an accident where they melt. But I mean, even the first one, we have passive decay heat removal. This means that we can actually, without having electricity or humans do anything, the heat will be removed simply by air conduction. So there's an airflow and around the reactor, and that removes the heat automatically. So it will never melt the containment. But just in case, there are 3 containments. So if the first one melts, then there's a second one, and then the second one there's also passive decay heat removal. And eventually the temperature of the salt will come below the 550 we talked about, and then it'll start freezing, and then it's not a problem.
So the question here is a little bit about if you have this fission products in there, do you remove parts of the fission products during the process? You can, for example, xenon and other gases are not really useful in a reactor because they catch a lot of neutrons. What is your process? Do you handle the thorium fluoride or the fission products during operation, or is that always completely in the container?
You're absolutely right. There's an important item here. For all the reactors we built to this day, all of them, they don't remove fission products. They keep the fission products in the fuel rods. And fission products is a little bit like the exhaust from your car when you drive your car on gasoline. But in a car engine, you get rid of all the exhaust every time the engine turns. But in all the reactors we've ever built, we kept the fission products or the exhaust in the reactor. And that's really bad, because it gives you horrible neutron economy. Like you say, especially xenon, and also there's some other elements. They capture the neutrons, and it gives you really bad neutron economy. And it's a little bit like driving your car with the brakes full on, like all the brakes on, and then you try to drive the car. And that is how all the reactors in the world are today. As an engineer, if you want to optimize things, it's horrible to look at that. But in a molten salt reactor, that's also what Alvin Weinberg said. In a molten salt reactor, you can remove those fission products. And when he talked about it back in the 50s and 60s, he said you can remove the volatile fission products. That means the xenon and krypton and a few other elements that will bubble out of the salt because they are in gaseous form. Yeah. And he thought maybe that's enough. But it's not quite enough just to remove the fission products that are gaseous. You also need to remove some of the ones that are dissolved inside the salt in order to make it a breeder reactor.
Yeah, and so you do that removal in your system?
Yes, we will not remove all fission products in the first generations of the reactor. Okay. We will try to, over the first 5 or 10 generations, we will try to remove more and more of these fission products. Okay. This is like an optimization process that is expensive and will take many years. But right from the beginning, we remove all the volatile fission products, just like Alvin Weinberg envisaged back in the 60s.
So for grilling fission
and
products.
And already that is much better than the classical reactors with the fuel rods where they don't remove it.
Yeah. So also in the human body, we remove a lot of our fission products.
We also remove the dirt from.
Yeah. So another point about this safety is that the size of a normal nuclear reactor is on a thermal side is about 4 gigawatt. Yeah. That is 4 gigawatt, and then we have the 7%, so it's still half a gigawatt of energy. If you shut down the reactor, and a half of gigawatt of energy, thermal energy is quite a lot. So your reactor is smaller.
Yes.
What about the size, the thermal size of your reactor?
Yeah, so you're absolutely right. Because it's only 2.5 meters in diameter, you cannot get gigawatts out of that. Yeah. So we can get roughly 100 megawatts of energy out of each one of these reactor cores. And then we also thought about that's not enough for a big power station. But our view is then you just put several reactors next to each other. And the great thing about that is then if one of them have a failure or have to replace one of them, then the other ones can keep running. One of the issues with classical reactors is that every 18 months you have to replace the fuel rods. Then you shut down that big reactor, the entire thing. You shut it down for more than a month, and then the electricity grid doesn't get energy from that reactor for a whole month. So all the different, for example in France, all the different reactors, it has to be synchronized when they take them out to refuel. Yep. Because if they were to take 3 or 4 out at the same time, then it will be a big problem for the grid. Yep. But when you have a lot of reactors like we want to have 10 or 20 next to each other, then you can shut one of them down and it doesn't really hurt you because all the other 19 or whatever is still running.
Yep. So now the point here is, so you can build more or less smaller reactors, and so it's if a moment the public is aware about small reactors or medium-sized reactors and the full-size reactors we are used. So you can scale the reactor by putting more of these containers side by side. So I will take a picture here from that. And so you can go up to a gigawatt still of electricity, but not by one reactor. You put 20 reactors or something like that there.
Yes.
Okay. What about the other processes like generating electricity? Is that very similar, or?
Yeah, so we decided when we had to create the company and talk about how do we want to structure the company and what is the strategy of the company, we decided that we do not want to run those steam turbines or something. So we have set up the company in a way where we sell the heat. We generate heat from our reactors and we sell that to the customer. And then the customer decides how they want to convert the heat to electricity if they want that. Some factories, they want industrial heat, so they don't need to convert the heat to electricity, but it's usually a combination. And those factory owners, they decide if they want to use a steam turbine or a Brayton cycle turbine or some other thing. So as a company, we don't make any decision on that. That's
you deliver the heat.
Yes.
Yeah. So your container, in short word, has 2 plugs.
Yes.
Hot and cold.
Yeah.
As our
yes, and it's correct. So we deliver the heat using salts. So non-radioactive salts. We send hot salt to the customer, and then when he has used the heat, he sends it back to us cold, and then we heat it up again. So the salt just goes around and around.
The salt circle is not the same as in the reactor. That is separated.
No, it's separated. There are, again, free layers, free barriers of separation between the radioactive salt and the salt that we send to the customer.
So the basic idea of this company is producing a lot of heat.
Yes.
Yes. And now...
and you can store heat also.
Okay, yes, and salt. Yeah.
If you have these giant tanks, you can store a lot of salt with heat in it. So you can store it for a couple of days if you want to.
So we can combine that, for example, with other renewables like sun, where only on day we have sun energy, and during night you can have additional stored hot salt that is already produced during the day, for example. Yeah. So that is one point. Now, one of the core discussions about nuclear is about waste management.
Yes.
So we are in Germany, we are looking for storing this waste for, let's say, 1 million of years. That is a very long period if you compare that period to the human society or the modern industrial society. It's 1,000 or even more times longer. How is it about the waste of this nuclear reactor? First of all, how long does this reactor work with one set of fuel, thorium?
Yes, so I want to make some comparisons here. The classical reactors, like you said in the beginning, the fuel rods can be used for maybe 18 months, then they take them out, and then they label them as waste.
Yeah.
But they're actually not really waste, they're still really valuable, but let's come back to that.
Yeah.
But normal reactors, every 18 months, they create a bunch of what is called waste in the media, which is not waste. But
okay,
and then they continue to make it. But in molten salt reactors, it's different because we don't want to throw the salt away. The salt is very expensive, so we want to continue to use that. And then we extract the fission products while the reactor is running. We talked about xenon and krypton, but there's also other fission products dissolved in the salt. So we extract those while the reactor is running, and that's the waste. But that's a different type of waste than the waste from classical reactors. The classical reactors also have fission products, but they are mixed in with plutonium and neptunium and other what is called transuranics. Yeah. Transuranics are all the elements that are with higher numbers than uranium in the periodic table. Yep. And they are always radioactive, and many of them have half-lives of thousands or 10,000 years. And this is why we say that we need to put it in deep geological storage, because if something has half-lives of 10,000 years, then it takes many half-lives before it has decayed to a safe level. And so it's easily become 100,000 years. And then you need to put it somewhere where it's safe for 100,000 years. And then people said, okay, we have to put it deep underground. But fission products usually have much shorter half-lives. They have half-lives in minutes or seconds or hours. Some of them have in days. And there's a few that have like 30 years.
Cesium 137.
Yeah, there's a few of them that has a little bit longer. But if you look at it in general, then after 300 years, the radioactivity level of fission products has come down far enough that you can basically put it back into nature because it's not dangerous anymore.
Yeah, it's in the natural nature radioactivity level.
Yes,
so if you are in some places, you have already that radioactivity, and that's similar.
Yes. So this means that we don't need to put it in deep geological storage. We can put it above ground for 300 years in a building with some fence around it. Or,
so the amount, the volume of that is also, if even in normal nuclear reactors, the volume of the waste is not compared to coal or something, coal ash or whatever. It is relatively small. So the whole German fixes more or less in one hall of. So we have this reactor. This reactor produces now this fission products. They can be separated and they can be stored, and up to 300 years until they completely decay. And then they have inside the reactor, there are some other metals. There are not a lot, but some plutonium, some others. How long does this core material work in a reactor?
Yes.
Beyond the separation of the fission products.
In an entire nuclear plant from Copenhagen Atomics, you have different things that last a different amount of time, but in general, we want to apply for the site license for 50 years. Okay. That means we ask to be allowed to run the reactor at this site for 50 years. And then some of the things inside have to be replaced. And in our case, it's mostly all the things made out of stainless steel. We talked about this corrosion before. Yeah. So all those things we would want to replace regularly, so say every 5 years. Yeah. So we have made it in a way where all the salts and heavy water can be unloaded from the reactor into some storage tanks, and then you can take the entire reactor with this onion core and the pumps and the heat exchangers and tanks. You can take that, and that's a little bit radioactive, so you put it inside the building, you put it in a place where it can radioactively cool down, and then you take a brand new reactor and you pump the salt and the heavy water back into that new reactor, and then that can run for another 5 years. So typically those reactor containers with all the stainless steel will last for 5 years. It's also the electronics and the software and all these things will also get replaced every 5 years.
So these containers are going in the backyard or whatever?
It's actually this one, right? So similar to this. This will be replaced every 5 years, but all the salts are for the whole lifetime of the plant.
So
and also the shielding,
like
there's a lot of shielding in there. Yeah. Also the shielding will be used for 50 years.
Yeah, so this is this cocoon, you call it?
Yeah, cocoon and also some other shielding.
Yeah, so you have this shielding. Now, another problem in nuclear production, we are usually talking about the problems in that area. I don't know, we are usually talking about the advantages, but we have already learned it's working for a long time, it seems to be cheap, dual use in some way, so that the people say, okay, can you build a nuclear bomb out of that material? Is that a dangerous topic that we should talk about, or is there any product that can be used at all in a nuclear?
Yeah, this is a very complicated topic, but we can sort of scratch the surface, and it's because we don't want to make nuclear energy for the good of people, to make electricity to the grid or make aluminium or whatever we want to use the energy for, and then at the same time produce some material that can be used for bombs. Yep. We would try to split the two, so we can only make aluminium and electricity and not make bomb material. But it's not that simple. It's when you have nuclear materials, there's different ways to handle them and use them for evil purposes. And maybe again, it's a little bit too much to go into it, but there are two different categorizations. So people talk about dirty bombs. Dirty bombs is not an atomic bomb, but it's a bomb containing radioactive materials. Yeah. And if you spread that in a city or stadium or metro system or something, then people will get really afraid, and they will, jump on each other, or what's it called, stamp each other to death. Okay. So that's the danger of that. It's not the explosion; it's the fear of the people that makes it dangerous. Okay. So that's the dirty bombs. Yeah. And that's one thing you want to protect the public about. Yep. And the other thing is, can some of the materials inside a reactor be used to make nuclear bombs? Okay. And basically, we've never seen any country make nuclear bombs out of materials from reactors. That doesn't mean that it's entirely impossible. That just means that it's easier to make nuclear bombs in a different way. And that's what they have done. All of the countries who have nuclear bombs, they have taken the easy route. And in molten salt reactors, it's a little bit the same. There are materials in there that you could potentially use for a bomb, but it's even more difficult to use those materials than use the materials from a light water reactor. So we are sort of moving in the right direction. We're not making it entirely impossible, but we're making it even more difficult than it was with the classical reactors.
Yeah, so that is because the amount of plutonium inside there
is very small.
And it is not easy to handle that material at all. Yeah. No. Okay, so that's one point here. Now let's look into the state of your technology. So the basic what we understood is that you have a molten thorium fluoride salt that is getting hot due to nuclear reactions. You can separate some of the fission products, and we use this heat usually we use heat for producing electricity combined with a steam power cycle, whatever. Yeah. Because you have a very hot salt in the area of 600 degrees, 700, whatever, this can be used also for some chemical processes. Did you think, or do you know something of that?
Yes. Yeah, we're looking at several different chemical processes where the heat can be used directly. If you look at the global market for those, so our reactor, the highest temperature inside our reactor is 700 degrees. And potentially in the future, we can get something out that is close to that, so 650, 680 maybe. And there are some chemical processes that can use that, but it's not like if you look at the economic value of the global market of those chemical processes, it's not a very high value. So there are some customers, and we will do that, but we also have to look at, are there some chemical processes at lower temperatures, like 400 degrees, and there are also some that can use temperatures at lower temperatures. And it would be great if we could get to higher temperatures, like 900 degrees or even above 1,000 degrees C, because then there would be more processes that we could use. And there are other companies trying to pursue something called high temperature gas cooled reactors. Yeah. It's exactly because they want to see if they can reach 1,000 degrees so they can make some of those products. So in our case, we cannot do that right away. But what we can do is then we can make electricity and then make electrical heaters to get from 700 degrees up to 1,000.
Okay, so you have a high starting
It's a combination, right? So you use some of the heat to make electricity, and then you use some of the other heat to start, and then you heat it further up with electricity.
Yeah. So it seems to be the first interesting market is the electricity market, because I'm quite sure that the electricity in times of no sun, no wind will get to high prices in the future. We'll see that. Yeah. So one of the big problems is rolling out something like that in our society, because it depends on the country. So Germany and Austria and Denmark are not pro-atomic. They have legislative rules that stop more or less every nuclear power stations. How is the situation here in Denmark? Do you have?
Yeah, so when I was part of the start of this, even before we started the company, so 15 years ago, when I was part of the energy debate, you could say, it was almost forbidden to talk about it. It was not that it was forbidden to build nuclear power. It was almost forbidden to talk about it. Like they said, no, we cannot have something in a panel debate who is pro-nuclear. This would be like really bad. But this has changed a lot. I think today in Denmark there's roughly 50-50 in the society of people who want nuclear power and people who do not want it. And we have a number of statistics. A lot of the people in the middle are sort of undecided, really. They are not strong for or against. But of course, like always, there are some outliers that are very much against or very much in favor of nuclear power. And they take a lot of attention in the debate. But most people are like, yeah, okay, if they can make it cheap and safe, then I'm okay. And if it's not in my backyard, that's usually also a thing in the debate.
So the point is now, if you are looking as a company for the market in the future, do you have some areas in the world where you say we could sell it easily? In some areas it seems to be very hard to sell.
We look at that a little bit differently, because with this new technology that we are developing and these thorium reactors, we're actually able to get the price of energy much further down than any of the other energy technologies. So we of course have coal and oil and gas, but we also have wind and solar and hydropower, and maybe someday in the future we have fusion. And if we look at those price points of all those different energy technologies, with the thorium molten salt reactor, we can make energy at much lower prices. So compared to classical nuclear energy, we can make it 4 times lower price, or a quarter of the price.
If you, in your papers, you write about 2 cents per kilowatt hour.
Yes.
That seems realistic.
That's really a game changer, right? And so when somebody comes with something that is that low cost, and the first question is, how much can you make of it? And that's back to this discussion we had a little bit earlier of the assembly line production. So could we make a lot of it on an assembly line? And of course we've looked into that, and we looked at sort of every year, if you look at the whole world, every year we build more electricity capacity in the world. And right now it's around 500 terawatt hours of electricity per year that the whole world builds. Oh, I should say outside of China. China also builds almost 500, but we don't really trust the statistics of China. But And also, we don't think that China is a market for us. We don't think we will be allowed to sell our reactors in China. So we just don't take that into account.
Okay, you're outside of China.
Yeah, so 500 terawatt hours, that is roughly the same as 60 gigawatts of baseload power. And we talked about before that some of the big nuclear power plants are, 1 or 2 gigawatts. So, it's just like 30, 40 of those in the whole world. That would be enough to make all the electricity that is the expansion of the global supply of electricity every year. But of course, we know that humans don't build, 30 or 40 nuclear power plants every year. We build maybe one per year or something. But in our case, we want to make this assembly line production. Yep. And of course, our reactors is a little bit smaller. They are only 100 megawatt of thermal power. So we would need to make 1,400 reactors per year, something like that, in order to deliver all the energy growth in the world or capacity expansion. Yep. And you ask yourself, is that possible to make an assembly line where we would make 1,400 reactors per year? And I think it's entirely possible. I mean, we already make more than 1,400 cars per day, or even per day, not per year. And I think...
Or trucks.
Yeah, trucks and I think airplanes, even airplanes, it's close to that, like 1,000 airplanes per year. So we can easily make 15 or whatever, 100 reactors. Of course, but getting the capital to stand up such a production is expensive. It costs many billions of dollars. Not as much as Corona, but like maybe 1% of what we spend on Corona. Then you can stand up a factory that could deliver all the reactors to serve all the new needs of electricity of the world. And then the question becomes, is that going to happen? I mean, it's possible, but is it going to happen? And I actually think it's going to happen. I think it's going to happen not in the next 5 years, but when we get into the 2030s, I think people will wake up and say, oh shit, we could, for a small amount of money compared to all the other big budgets in the world, for a small amount of money, we could stand up a factory that could deliver all the energy we need in the entire world at low cost.
Yeah, so the problem in nuclear power stations, at least in the conventional area, is the red tape cost or to get a license to produce that. Yeah. So we have seen some reactors built very fast in Dubai. They had 8 years or something like that. And in other countries, we have seen more than 10 years. But the question is, what is the time you need when we have, let's say, a green field, and now you have to deploy a new nuclear power station with your technology? Yes. What is the technical time you need to set up that, and what will be the permit time? So let's go to the technical time, because
that's one of the things we want to demonstrate. We're going to run a small test reactor in the next couple of years. And one of the things we want to demonstrate there is that we want to show the world how quickly we can set it up, run it, and take it down and move it. So we will build it here in Denmark, but Denmark currently, because of the government and everything, we don't have a regulatory authority that have the credentials to approve starting a new type of reactor. So there's not even a government department who could do that. And that would take time to set that up. So we go to another country and test the reactor. And one thing is to test that the technology works, but another thing is to test that we can actually set these reactors up in a short amount of time and take them down again. So that's both of those things we are going to prove. We will build the reactor here in Copenhagen. We will test it here, not with the reactive chain reactions, but we will heat it up with electricity and show that all the pumps and everything is working. Then we will disassemble it, move it on a truck to another country, set it up there in about a month, and then we will run it in another country for 1 month, and then we will take it down again and move it back to Copenhagen and set it up and run it again with electrical heaters. And in that other country, we will run the real chain reaction so that we can show that this thorium fuel cycle actually works, because there's also still some people who are a little bit skeptical if it works as well as we say it does. And of course, to be honest, we have only done simulations, and we trust the simulations, but I accept that other people do not necessarily trust our simulations. They want to see with their own eyes that it actually works.
Yeah,
so
but you see the time period is in months. You count in months.
And that's exactly, and that's what we want to prove in roughly 2 years from now, that we can do that we can set an entire reactor up, we can run it and take it down again and move it. So if we can show that we can do that, then I think it's obvious to everyone, okay, maybe it's not from a technical point of view difficult, but maybe there's some red tape, like you said, maybe there's all this fear about not in my backyard and everything. And I do imagine there's 200 countries in the world. I do imagine that at least in 100 countries it will be impossible to set up a reactor in 1 year, just because the way the governments work in those countries. But I also think that there are some countries. Let's say in the beginning maybe we can only find 5 countries where they are able to allow us to set up a reactor in 1 month and run it.
But then you can show that it is fast set up, and you can show the low price.
Yes, then we can start in those countries who have a reasonable approval process. And then later on, like you said, Germany and Denmark and Austria, I don't know. Some of those countries might be much slower. And then we will have to wait. I mean, in 50 years, maybe they change their mind. And then maybe we can install nuclear energy in Germany. Maybe. I hope it doesn't take 50 years. But
we will see. We will see.
Yes.
We have now discussions about that topic because we have shut it down, all our power, but the power price is now very high. It's definitely beyond 2 cents. And comparing it with solar energy, because people often say, okay, solar energy is depending on the country in the same range, but it is not a 24-hour service.
Yes.
You have only in that short period of time when the sun is shining, and it's definitely always never at night.
And for Germany, there's also another possibility, actually, because all the countries around Germany, except Denmark, all the other ones around are planning to build the nuclear power or already have nuclear power. Yeah. So you could put 100 gigawatts in Poland, 100 gigawatts in France, 100 gigawatts in the Netherlands, whoever, and then they could supply to Germany. So you don't have to build it inside Germany.
That's a very interesting
And then
idea,
those other countries, they could have a 10% tax because they are helping.
Yeah, so at least in Europe, the convention is that nuclear power is a green technology because that is one point, that it has no carbon imprint. And some discussions I have learned is that the carbon imprint of nuclear power stations, some people say it is very high. I doubt about that, but have you any idea about the carbon impact of your system? Did you ever check that?
Yes, so when you burn the nuclear fuel inside the reactor, there's no carbon dioxide or CO2 created. So the chain reaction or the physics behind the process creates no carbon at all. But there's always this discussion about the transport of the fuel and the transport of the concrete and the steel, and also making concrete and steel creates a carbon footprint. So you cannot say that it's zero because there are this transport of the materials, but usually classical nuclear power plants, they last for 60 years or something. So you have many, many years to sort of pay back with green energy to sort of get the carbon price down. But you're right, if you look at the first hour, so if you build a nuclear power plant and you look at the first hour and you say all the CO2 that you had for transport and concrete and steel, and you put that into the first hour of operation, then then you get some high values. So some people in the debate has been cheating by doing things like that with the numbers, and they say, if you only look at the first hour or the first year, then it looks terrible. But I think you should look over the entire lifetime of the plant. But there was, unfortunately, both in the US and in Austria, there was some nuclear power plants that were built, like they built the whole power plant, and then they never got the approval to start it. And then, of course, you spend all the carbon to make all the steel and transport, but you never start making any green energy. So then, if you look at that calculation, it looks terrible. But that's why in the debate there's some discourse.
Yeah, because I was really surprised about these high numbers, and I've learned that the realistic numbers are in the area of, let's say, 5 grams of carbon per kilowatt hours, and in a coal, it's a kilogram or even more.
Yes. For Copenhagen Atomics reactors, the amount of CO2 per kilowatt hour is a little bit smaller than classical reactors, but it's very
yeah, because
different.
you have not
it's
such
almost,
a lot of concrete.
but it's almost the
housing.
same as classical reactors.
Yeah. So now the regulations for reactors are not only because you have to be in Germany. It's very difficult or even impossible in the moment. But there is an international atomic agency that is controlling all the nuclear powers, at least in the Western world or in the whole world.
No, not really. So I think you're thinking about the IAEA, the International Atomic Energy Agency in Vienna.
Yes.
That was originally created out of the UN organization, and IAEA is supposed to look after the Non-Proliferation Treaty. And the Non-Proliferation Treaty is a treaty signed by almost all countries, like more than 180 countries have signed that, and they say we want to sort of make sure that we don't use nuclear materials for nuclear bombs, and we should try not to get information and materials to countries that do not already have nuclear bombs, so that more countries get access to this technology. So there's an international agreement that we should limit sort of the spread of materials and knowledge how to build nuclear bombs, but at the same time we should allow countries to have nuclear energy. Yeah. And that's the mandate to IAEA in Vienna, and this is a little bit difficult mandate because on one hand they have to limit the use and spread of this, but on the other hand they have to help new countries who want to get nuclear energy to get it in a safe way. So IAEA doesn't actually approve reactors or they don't. It's not IAEA who controls the fuel or anything. But they have the right to go to any of those countries who signed the Non-Proliferation Treaty and make inspections. And maybe you remember back in Iran and other places, they were able to come in there with the inspectors and look for if they were misusing the materials. And they can do that in all countries. So they have that mandate. But they actually don't have a mandate to approve nuclear reactors.
Who has to approve it?
Well, right now it's a nation-state problem. And in this Non-Proliferation Treaty, all the countries have said that, they want to make sure that they use nuclear materials in a safe way. Yep. And so if you build a reactor, you have to make sure that the people who handle those materials, they do it in a safe way. And there are some international guidelines on how each country can secure that. And sometimes they follow those guidelines, but they don't have to. It's always each country have to make the approval. And then in a few cases, there has been countries that are good friends where they help each other. So maybe the approval authorities from one country help to approve a reactor in a neighbor country.
Okay. So let's say you want to install that technology, let's say in Poland.
Yes.
And then can Poland approve that, or would the approval be done?
So Poland already have a nuclear regulator. Because they have some test reactors in Poland, and they also plan to build more big nuclear power plants. So Poland already have a nuclear regulator that has some laws and some rules about how they can approve a nuclear reactor in Poland. Yeah. And we've talked to them, and potentially we could build our reactors in Poland.
Yeah. And then if you have a permit for, let's say, with your technology for one country, then you go to, let's say, Finland. They can accept that, or
unfortunately,
there's no fast track.
Unfortunately, as far as I know, there's no country right now where an approval in one country automatically give you approval in another country. Yeah. But there are people who are working towards that, and there are countries that are working together to see if they can make sort of rules that are so similar that what is approved in one country automatically makes it approved in another country. It's for airplanes and cars. It's like that. If you build a car in one country, you don't need to get that approved in another country. It's already automatically approved.
At least
and also with airplanes. As soon as the airplane is built at Boeing or Airbus, then you can fly to Denmark and it's okay. But with nuclear reactors, it's not like that yet, but someday maybe.
Okay, so in the moment then the nuclear reactors can be produced, and we have some type of mass production, then it would be necessary, because otherwise the mass production gets very expensive. You have to approve that for, let's say, 100 countries where you can...
Yeah, but I think actually what will happen is we will not install this in 100 countries. I think in the first 10 years of this technology, I think we will install 99% of it in 5 countries.
Yeah, okay.
The first countries to adapt this technology, because what happens is that those countries who's already adapted it, the risk of getting this approval goes down.
Yeah, okay.
And then in nuclear energy, risk is always a big factor on the interest rate of the money you want to borrow.
Yeah.
So then those countries become very competitive. And this is also what we're seeing now in Abu Dhabi, because they already built 4 reactors and they did it in a small amount of time and at a okay budget. Now people want to build more reactors in Abu Dhabi instead of maybe Oman. They say, no, because if I want to do it in Oman, then there's a risk of how long does it take. But now I know that in in Abu Dhabi,
it works.
We can do it in 4 years. So the risk is much smaller. So now people want to build more reactors in Abu Dhabi. And the thing, if you have lots of energy, then you want to make aluminum or ammonia or hydrogen or some of these commodities, and you can just put those on a ship and sail it to Oman or Germany, so you don't need to make the aluminum in Germany. You can make it in Abu Dhabi, for example.
You attract the industry for the low energy price to the countries where you have a lot of nuclear power, because you can produce 24 hours.
Yes, and I think this will happen also to Copenhagen Atomics. I think, like I said, 99% of the reactors will be installed in 5 countries. I don't know which those. Of course, I have my own internal list, but I'm not so confident that I will share it with you. I don't know who those 5 countries are.
Yeah. We can make some guesses. So people can guess that in our list of comments in this video. So now that is the point now is the timeline of your company. So you are in the moment you are starting to develop all these details like the pumps and materials and so on, and even produce some lithium, cleaned lithium I've seen.
Yes.
And then what is the next step? So when will we see the first reactor with, let's say, low power running on your technology?
So I think by the end of 2026, we will be able to start the first test reactor.
2 years?
Yes, and that's just a demo. Well, it's 2.5 years because the end
Okay.
But it's coming soon, and we're already building the test reactors here and testing them here at this headquarter in Copenhagen. And like you said, we are making all the salts that we need and pumps. We're making lithium-7 enrichment. We're making the pumps that we need. So I think it's possible in 2026 to have the first demonstration reactor, and then I think a few years after that, we will be able to make the first commercial reactors. And then, of course, from then on, we need to optimize it and make it the price lower and increase the production.
Yeah. So you have a timeline where you see, let's say in 2 years we'll see the first test reactor, and then we'll see this maybe a commercial site. What would the time take be for a commercial site?
I think 2029 is 2029. That's when I find likely that
something like 6 years or so, 5 years. And then this 5 countries, whatever list you have in your mind, is starting to develop a lot of that.
Yes.
So when you start your serial production and you deliver that to this first countries who are accepting that technology.
Yes.
Do you think for the long term now, is there an impact to our greenhouse gas problem? Do you have the idea that we produce so many of these molten salt reactors, of the Copenhagen Atomics thorium reactors, that will have a real impact on this problem of carbon?
Yes, I think so. I gave a talk just a few weeks ago in another conference, and there I said that I think before we get to 2100, then more than half of all the energy in the world will be made from thorium, and that's quite a aggressive prediction, because today we make no energy from thorium. So to be here like one guy saying in 75 years we will make half of all energy from thorium, that is very aggressive statement. But I think so, and of course it's up. People have to make up their own opinion about that.
Now you are not the only company in the market who is developing new technologies. So do you see that many others are on track or are faster or have a better technology? Anything about them?
No. So we talked about in the beginning how it's difficult to make this neutron economy so that you can that you can make energy from thorium. We also talked about that you cannot put thorium in classical reactors.
Yeah,
it doesn't work.
Yep.
I don't see a lot of companies trying to do what we are doing.
So
I mentioned
thorium,
one other. I mentioned this Flybe Energy. They're doing it. There's been a few other companies talking about it, but I've not seen any proof that they're actually going in the right direction. They need to put something on the internet or out in the media that proves that they're going in the right direction.
So you have already done a lot of experiments here,
yes,
especially the pumping technology. The pumping for the internal movement of this liquid salt. You can do that.
Yes.
Are you working together with other companies, or are you thinking about collaboration, that you are maybe Siemens or big, no, Siemens maybe not a good name because it's not in nuclear at the moment, other nuclear companies who are interested in that?
Yeah, we do have some collaboration with a number of big companies, and we also have collaboration around the technology with a long list of universities and national labs.
Okay.
And
cool.
so on the technology side, I would say we're mostly working with universities and national labs. There are a few also molten salt companies that we're working with. But on the, you also mentioned companies like Siemens, and one of the ones I will mention here is we have a collaboration agreement with another Danish company called Topsoe. Topsoe is the #1 company in the world making ammonia, and ammonia is fertilizer. So they don't make the fertilizer, they make the plants, or the factory that makes the fertilizer. And they are #1 in the world in making those types of plants, and they've been doing it for 80 years now. So we have an agreement with them because, of course, fertilizer is needed for all the food, for all the 8 billion people. And Topsoe also recognized, okay, if we can make fertilizer green, because in the past, all the fertilizer was almost like 99% was made from natural gas. And natural gas, of course, is a CO2 pollutant, or it makes CO2 in the process. So this company, Topsoe, wants to move away from natural gas and see if they can make fertilizer that is green fertilizer. And of course, they realize that, if they can work with Copenhagen Atomics, then we can make all the fertilizer and all the food in the world become made from green energy. And this is a giant opportunity. I mean, that opportunity alone is much bigger than if you could sell all the electricity in all the European electricity market.
Okay.
So it's a much bigger market in terms of energy consumption. So of course we are very interested in that, and we have a collaboration agreement with them, and we're working towards making the future ammonia plants with nuclear energy.
Very promising. Sounds very promising. Yeah. You talked about universities and other research institutions here in Denmark or international?
Mostly international. There are collaborations in Denmark as well. But for example, we work with several of the national labs in US and also UK and Korea and other places. And also a lot of the well-known universities around the world. We work with them. And there are a number of molten salt startup companies also. And especially, so there's some of the technologies we make that we want to sell, and others we want to keep for ourselves. But one of the ones we want to sell is this lithium-7 that we are making, and that helps a lot with making efficient salts for molten salt reactors. So we're already in dialogue with a handful of companies who are interested in buying salt from us. So we have these two things. We have lithium-7, which is difficult to buy today. There's not a lot of production of that. So that's something that we want to make and sell to potentially competitors. And then also the purification of the salt. I talked about how to reduce the corrosion in the beginning. So that's another thing we also want to sell, the service that we can make these salts already with a very low content of moisture and oxygen, so they are not corrosive. So those are some of the things where we're collaborating with other companies.
Okay, now if we hopefully can produce this nuclear power from thorium, that is a long-lasting material that we have enough for thousands of years, then the problem is in the moment, in some global scale, the misconception about nuclear energy in many countries and in many people's mind. I want to talk a little bit about that misconception. So if you are looking at your personal life, have you ever been anti-nuclear, or have you ever always been pro-nuclear? Or
so in Denmark, there was a very strong anti-nuclear movement back in the 70s, and I think that mostly came from the fact, or I know I talked to some of the old people that were part of that. They said that we were really afraid of these old people in Russia and US with a hand on the button to start a nuclear war. Yep. So they were super scared, and sort of Denmark is right in the middle between US and Russia, I think. So they were scared of that, and that's why they wanted to make this anti-nuclear demonstrations. It was not really against nuclear power, it was against these weapons and the Cold War and all of that. And they thought we had plenty of energy back then. I mean, there was no worry about CO2. So they thought, why don't we just use oil and gas and coal and wind and solar? We had a little bit of wind back then. So the majority of the people in Denmark said, no, let's not make nuclear energy. We're such a small country anyways. We just want to make, coal and oil and gas and wind. And they went down that road, but I think now people are starting to realize that, it's not really a good solution. Denmark is a small country, maybe it can work here, but they realize that it cannot work for the rest of the world. And there's also people in Denmark who think that Denmark should have nuclear power. So maybe eventually we will get that, I don't know. But already today we have, electrical cables to Sweden and Norway and Germany and Finland and everything. So we already, especially from Sweden, we get a lot of nuclear energy when the wind is not blowing. So I mean, we already have the benefits of nuclear energy, even though we don't have any nuclear power plants. So,
okay, that's because the international exchange of energy is now very obvious. And so one misconception sometimes I think is about the danger of radioactivity. You have said you shielded your concept very well. So outside the energy production hall or outside of the nuclear reactor, we have no danger at all from the radioactivity.
Yeah, so normally when the reactor is running, when there's just normal operation, there's a very, very low limits. In the nuclear industry, we always say at the fence, because nuclear power plants always have a fence around them. And at the fence, you have to be at a very low level of radioactivity. And of course, we have to also comply with those rules, and we can do that. That's not a problem. But so there's no danger to the neighbors who live there. Then the question is, okay, but what if it's not normal operations? What if there's an earthquake or like tsunami or airplane strike or whatever, and there's an accident? What is then the risk of the neighbors getting radioactivity? And that risk, you cannot get that down to zero. I mean, there will always be a risk of some sort of accident or meteor strike or whatever. And of course, different countries actually have different rules about how low that probability have to be. And also sometimes they have rules about how you have to calculate that probability. Like what is the likelihood of an earthquake or likelihood of an airplane crash? And then all these different likelihoods, you have to calculate the statistics. And typically it's very typical that you say if you were to operate this reactor for 1 million years, then you can have one accident.
Okay.
So that's sort of the statistics of how often it is allowed to happen. Or otherwise, if you put 1 million of these reactors in your country, then you can have one of them fail every year. And then of course the people who live right next to that, then they will have a higher level of radioactivity. But the public or the government say that, okay, we also have to accept that the nuclear power station brings a lot of good to the society. So we are willing to say that if it's only one accident in 1 million years, it's an acceptable level. And that's the way it's calculated. But in different countries, different rules about these calculations.
We have to compare it with other risks like a coal power station. So do you have any idea about the danger of a coal power station compared to a nuclear power station? Yeah,
there's a lot of statistics made on this internationally and shared among countries. And if you look at for the whole world, I know that there are some coal power stations in different countries are maybe more or less filters and stuff. But now we just have the global average. So for coal-fired power plants, they kill 1,000 times more people per terawatt hour of electricity than the average nuclear power plant. And we have to remind ourselves that
that is including this Chernobyl event. And,
yes. Yeah. The reactor that blew up in Chernobyl is a specific type of Russian reactor. And we still have 8 of those reactors operating today. And they have been running now for 40 years, and they have not killed anyone. So, I mean, even those reactors that were, maybe not the best design, we're still using that for 40 years and haven't killed anyone. And I just want to say that there's no coal-fired power plant anywhere in the world that can claim that it hasn't killed anyone. I mean, all coal-fired power plants have killed people. Yeah. So it's coal-fired power plants are clearly much more dangerous to the health and also killing people in terms of mining, transport of the coal, and explosions, and also all this coal dust. So you have the chimney, and you have the coal ash or coal dust coming out of the chimney.
Yeah. So the point is the safety on the long term of nuclear power stations is higher than comparable 24-hour on stations we use today. Yes. That is one of the statements. Now, we have gone now through all these interesting parts of your company. So where do you think you are in 15 years from now with your company? What is your vision, how that will work, and how it will be accepted by the market?
Of course, it's always big question is how well does the technology work, and how quickly can we bring it to market, and also, like you say, how will it be accepted by the market? But now you get my version of it. I think it'll take another 5 years, like we talked about it before, before we can get to the first commercial reactors. And 5 years is a little bit like when people had the first cars. I mean, today we have billions of cars, but in the beginning they only had 20 or 100 cars. That's when we get to the 2030. We have sort of the first 10 maybe of our reactors, and then we will have to scale that up and get into production. And I think that will take at least 5 years to scale the production. So maybe in 2035 we will start to have a bigger production with hundreds and maybe even thousands of reactors. But still, I mean, even 1,000 reactors is a very, very small percentage of the global energy supply. So we need to go beyond that. And I think it's really, really important for us as a company to prove that we can get the price down. That's the most important thing we need to prove, to get the price down so that nuclear energy becomes a lower price than other sources of energy, coal-fired power plants or whatever. So if we manage to get the price down, then I think the market will also request us to build a lot more of it. And then, of course, we need to scale up the production to meet the demand from the market. And again, it takes maybe another 5 years. And then we have a very a factory that can make a lot of energy installation because the price is low. We can mass manufacture, and we can also show that we can install it in less than a year. That's also another important thing, because even if we could make a lot of it, if it takes 10 years to get it approved and installed, then I don't think people will buy it. They will continue to buy coal-fired power plants or whatever. So it's really important to get the price down, to be able to mass manufacture it, and to be able to install it in less than 1 year. And I think when we get to somewhere in the late 2030s, we will have proven that, and that's almost 15 years from now. So yeah, by 2040, we should be in a good position with being able to install thousands of reactors every year.
Okay, so any wish for the future?
I would wish that people would look more at the math and physics of things instead of, I think there's a lot of fear-mongering, and there's a lot of, in media, it's like a popularity contest that somebody wants to say something and then they want people to follow them, like a YouTuber, or what is it called, influencer. I think it's called influencer, right? So I don't think you should be influenced by people. I think you should look at the math and the physics and see if it's tell you the truth. And if it doesn't tell you the truth, maybe it's not correct. And I think there's too many people, especially in big media and politics, that just follow somebody because they said something that most of the time doesn't make any sense at all. So that's my wish for the future. More math and physics.
Yeah, thank you for this statement. So, you know, I'm from physics background. And to our listener, thank you for attention. This was our first test to have an English talk in our Energy Gespräche that we have. Hopefully you liked that. If you like it, put your thumbs up and take an abo, or give us some comments about that if you liked that and what was special about that. So thank you to Thomas Pedersen for this, your time, your scare time, and thank you for all this background information about Copenhagen Atomics.
Yeah, thank you for being here. Thank you.